Welcome to the structure analysis one. We are going to start new chapter displacement of statically determinate structure, in which we are going to cover member bending in circular arc, relation between slope and deflection and radius of curvature, method of slope and deflection at a point, double integration method, deflection of cantilevers, deflection of simply supported beam, McLaurin's method, moment area method, conjugated beam method, and deflection by strain energy. Introduction of the chapter. A beam when loaded gets deflected. It is but obvious કે કોઈ પણ બીમને લોડ આપવાથી એમાં માઇનોર પણ ડિફ્લેક્શન તો થાય જ છે. The cross section of the beam displaced perpendicular to the initially straight axis of the beam and at the same time rotated. The axis of the loaded beam bends in a curve which is known as elastic curve or deflection curve. Definition of a point on the axis of the beam is vertical distance between its position before loading and after loading. Deflection of a point on an axis of the beam is the vertical distance between its position before loading and after loading. The angle through which the cross section rotates with respect to the original position is called the angular rotation of the section or slope. Again, the angle through which the cross section rotates with respect to the original position is called the angular rotation of the section, or it's also called a slope. The amount which a beam deflect depends upon its cross section and the bending moment, or it's called load also. The following are the two design criteria for the deflection of a beam: strength and stiffness. As per the strength criteria of the beam design, it should be strong enough to resist bending moment and shear force. As per the stiffness criteria of the beam design, it should be stiff enough to resist the deflection of the beam. Now, first, member bending into a circular arc. We can show a figure, so a beam AB of span L subjected to a uniform bending moment M, so that the beam is bent to a circular shape A, B, and D, or ADB. Let R is equal to radius of arc. Delta is equal to CD is equal to deflection at the center of the span. By property of intersecting chord of a circle, AC, CD, CE, AC, CB, CD, and CE. Okay. Now AC is equal to L by 2, CB is equal to L by 2, CD is equal to delta, and CE is equal to 2R minus delta. Okay, so simplify it. L square divided by 4 is equal to 2R delta minus delta square. For a practical beam, the deflection delta being a small quantity, delta square can be neglected. That's why we can uh, simplify it as a 2R delta is equal to L square divided by 4. Pivot the delta is equal to L square divided by 8 into R. From the relation M upon I is equal to E upon R, we can also study this relation in mechanics of solid. So R is equal to EI upon M. Put the values of R into above equation. L square divided by 8R is equal to S square divided by 8 into M upon EI. So delta is equal to M into L square upon 8 EI, which is a maximum deflection of a beam. The maximum slope theta at A or B equal to angle AOC or BOC. Let us see AOC or BOC. Sin theta is equal to AC upon AO is equal to L upon 2R. Since theta is also small quantity, neglect theta in a radians. So theta is equal to L upon 2R. But we know that theta is equal to L into M, 2 into EI. So theta is equal to M into L upon 2 EI, which is a radius, which in a radian, and that's the maximum slope. Now another theory, relation between slope, deflection, and radius of curvature. Consider a small point or a portion of beam PQ bent into an arc as shown in figure 5.2. Let us see the figure 5.2. Here they consider a small portion of the beam which is curved. PQ is taken, ds is equal to length of beam, PQ, radius of arc, r is equal to c is equal to center of arc, pi, c is equal to center of arc, psi is equal to angle which the tangent at P makes with XX axis. Tangent psi plus delta psi is angle which the tangent at Q makes with x axis. So for the geometry of the figure, we found that angle PCQ is equal to d phi. ds is equal to r d psi. We know that if x and y be the coordinate of point P, then tan psi is equal to dy by dx slope, sin psi dy by ds, r is equal to ds upon d psi is equal to ds upon dx, d psi upon dx, sec psi divided by d psi upon dx. cos psi is equal to dx upon ds, tan psi is equal to dy upon dx. Differentiating with respect to x, we have sec square psi into d psi upon dx is equal to del square y upon del x square. Simplify it, we can get d psi upon dx is equal to d square y upon dx square upon sec square psi. Substituting equation 2, we get this equation r is equal to sec cube psi upon d square y upon dx square is equal to sec square psi 3 by 2 divided by d square y upon dx square is equal to 1 plus tan square psi. Sec theta is equal to also 1 plus tan theta. So convert it into 1 plus tan square psi into 3 raised to 3 by 2 divided by d square y upon dx square. The slope tan psi at any point is a small quantity, hence neglected. So neglect the psi terms. So we can put in a r term rest of the data 1 upon d square y upon dx square. We can say d square y upon dx square is equal to 1 upon r is equal to, we know that for curve beam we know that m upon I is equal to e upon r. So 1 upon r is equal to n upon ei curve beam. So put this value in this, we can get m is equal to ei into del square y upon dx square. So ei into d square y upon dx square is equal to m. This is a differential equation of elastic curve. It should be clearly borne in the mind that the above equation takes into account the effect of bending moment only. The effect of shear on deflection is extremely small and may be neglected. Sign convention for the is damn similar to the same. We can continue our lecture with method of slope and deflection in the next chapter.